Hand back the exams at the end of the hour. Fundamentals of electrochemistry. Okay. I've always liked electrochemistry. It seems very clean. But how do you prevent rust? Well, sacrificial anodes, right? So, and we talked about this in general chemistry, but you may not remember. And so we'll review a few things, but electrochemistry is good for a lot of stuff. I mean, biochemical sensors. That's how you get aluminum cans, right? It's through electrochemistry. But let's talk about, see if we can remember how to do some of this stuff. Assignment of oxidation numbers of atoms in the compound. There are some rules. Determining oxidizing, reducing agents, that sort of thing. So here's the rules. So let's see if you remember them. So you've got them there in your notes. So you can read over them if you forgot. Marlena, we want to find the oxidation state of each element in potassium chloride. Okay. Where do you start? Do you remember this? Okay, let's stop right there. She's exactly right. Now, how did you know that? Periodic table, that's the charge of it, right? K can only have one charge, plus one. So then chlorine, Desiree, has to be what oxidation state? -1. And why is that? And I'm circling my answers here. Why does it have to be -1? Not really. Because chlorine can take on a number of different possible oxidation states. In fact, I should have had it in here. That the sum of all the oxidation states has to equal, not essentially 0, has to equal the charge, or whatever it is. And you're right, 0 in this case, potassium chloride, there's no charge. Okay, how about carbon dioxide? Jeff, where do you start there? Each oxygen's a -2. So that means I have a total of a -4. So carbon must be what then, Andy? +4. Circle my answers. How about the next one, Gloriana? What's the oxidation state?
Oxygen is -2 for each of them.
I'm talking about this one.
Oh.
Yeah, just +3. Kind of an easy one. Nitrate. Ricardo, where do you start for nitrate?
Oxygen.
Oxygen's got to be -2. I've got 3 of them for a total of -6. So Sabina, what does nitrogen have to be? But we want a -1 charge, so it'd be +5. I think you guys remember this, right? So that's the game that you're playing. And well, let's just finish it, right? Kelly, where do you start for vanadium 5 carbonate? Oxygen's -2. Now, what we could do, if you like, you can do this. Because what's the charge on carbonate? It's a -2. So you could figure out carbon and oxygen just using this. Because this is definitely carbonate, right? And sometimes it's easier by pulling out that polyatomic ion. And we did that. Oh, no, we didn't do it already. But that's -2, -6. Carbon has to be positive. What, Danielle? What plus the -6 gives a -2? All right. +4. There we go. +4 and -6 would be -2. So that means this guy's +4. He's -2. And vanadium, just looking at it, you know it has to be +5. Here's a charge right down there. But you can do the math and check, but it works. Okay, how about this agent stuff, Brandy? Oxidizing agents are always reactants and always get reduced. Reducing agents, Mel, are always products. Everybody agree? Reactants. They're the agent. They're inducing the change. So reducing agents are always reactants. And they always get oxidized. Okay. Determine the oxidizing and reducing agent in the below reaction. Oh, we didn't do sulfite. So figure out, pick one. Now once you figure out, let's say you figure out what sulfate is, if sulfite is turning into sulfate. If sulfite is getting oxidized, it has to be the reducing agent. So then you don't need to mess with chromate. If it's the reducing agent, this has to be the oxidizing agent, right? So just make sure, see what's going on here. See if you can figure out which is which. So just mess with chromate or mess with sulfite. Figure out the oxidation state of this stuff. O never changes. Yes, Sabine?
This isn't a stupid question, but like, how are oxidizing agents and reducing agents on the same side?
Because if this is an oxidizing agent, he's going to cause this guy to get oxidized. This is I'm just pretending. We got to finish this. If this is the reducing agent, he causes that guy to get reduced. He's the agent. And thereby he gets oxidized in the process. So reducing agents get oxidized. Oxidizing agents get reduced. Let's see. 3 times -2, 6. I messed with sulfite and sulfate. Is that what you got? Did you get +4 for sulfite going to +6? Anybody else? If anyone else messed with it? So Desiree, whether you got that or not, this compound got what? It got oxidized. So this compound is the, everybody, reducing agent. Don't even need to mess with it. This has to be the oxidizing agent. Okay.
Do you want us to put the numbers above it?
I would, since exams and all these things get graded partial credit, you gotta, you should show your work, otherwise you get nothing, right? And if you want to get more points so I can understand what you're doing, you can circle your answers for oxidation states. If you don't, I'm not going to have a clue what the heck you're doing. You'd have to write something like S equals +4, O equals -2, right? Then I could see what you're doing. But there isn't a whole lot of partial credit to give on something like that anyway. Charge, current, voltage, and power. So see if you can figure out what the standard metric unit is for those. I forgot something. Okay, how about charge? What's a standard metric unit for charge? It's a coulomb, and it's abbreviated big C. How about current? Amp, big A. Voltage? Monica? That's this one. Big W. Voltage is volts, big V. Oh, I guess we could have done, sorry. I'm doing the wrong thing here. Mathematical symbols down below. Oh, that's okay. Charge, so coulomb. All right, amp, volt, watt. Okay, so all right, okay. How about the mathematical symbol? I don't know if you ever had physics. Charge, they always like to use what? Little q. How about for current? Capital I. Volts, big V. Power. I've always seen it as, what have you guys seen it as? I saw capital P is what I saw. Okay. Current is charge per unit time. Therefore, an amp is what unit over what unit, Kelly? Yeah. So S for seconds, and charge is, that's a symbol, pretty much, yeah, big C. Voltage is electrical potential energy per unit charge. So, Jeffrey, a volt is a what over a what? Joules, good. Joules for energy. Over Coulomb. Okay. So voltage is just top of the hill, electrically speaking. So if I can, all right. So at the tip of this is very high voltage. It's electrically speaking, it's the top of the hill. Balls like to roll down hills. Well, likewise, this is high, very high electrical potential energy. So I can actually rip the air apart, and that's where you hear the snapping sound. The snapping sound is when the air actually slams back together, because air has to get torn apart for the electrons, for the plasma to travel from here to there. So the sound is, that's what thunder is. Thunder is, air got torn apart, but it's slamming back on itself. But I kind of like this idea better. Do you know how these work, these fluorescent tubes? It's fluorescent, so that means something has to be emitting light. That's what fluorescence is. So you've got this white powder in here, and that's why it looks white. And then it's evacuated. It's a pretty low pressure, but they have a gas in there. And what happens is that gas, they're slamming into each other once in a while. It's probably like argon or something like that. But it's nonpolar, right? So. But the idea here is somehow let's get those gas molecules in there, argon, whatever it is, to really accelerate really fast, slam into this white stuff, so the white stuff will emit light. So how do you get the stuff to accelerate? Well, if you have one, and since these are not ideal gases, if you have one argon atom slams into another argon atom, or if an argon atom, more than likely, if it's not very high pressure, it's going to sit the sides or whatever, the electron distribution changes a little bit. It's not perfectly nice and symmetric anymore. And just for an instant, a very small instant in time, they call it an instantaneous dipole. Well, in that instantaneous dipole, they have a huge voltage across here. So that little argon, somehow its electron distribution is no longer nice and symmetric. It runs into something, gets messed up a little bit. There's a slight dipole there, and man, it just accelerates, right? To whichever end, the plus or the minus end. So that's all I'm doing is taking advantage of here, is I'm accelerating the argon atoms. They're pulling in, because those instantaneous dipoles are always there, but there's nothing there to give them some energy, voltage, to get them to accelerate, right? And then they'll slam into the side and fluoresce. Okay, a Faraday is the total charge on a mole of electrons. See who remembers this. A Faraday is how many coulombs? Starts with a 9. 96,000. Ooh, Brandy. Bonus points. 96,485. Good job. Typical relations. V equals IR, P equals IV. Work equals V times Q. Okay, that's the kind of stuff we did. So that's our little introduction. Galvanic cells. This is what we're all about. Okay, you're stuck on a desert island. You want to generate some electricity and power your little reading light so you can read a book. The electrochemical cell to the right can be described by the chemical reaction. Okay, so overall, you have one half reaction or one cell, right? Something's got to be producing electrons, and something else is reacting with electrons, right? So something's producing them, and something else is reacting with them. So then there's your current. Generate a little bit of voltage, right? So they're separated. It's not going to do any good. I mean, you can't stop the reaction. If I could dump these two guys together, but then the electrons are just being converted, in the solution, like a regular typical reaction. So it's not going to do you any good. You can't light any light bulbs. So that's why you got to have to separate the two half reactions, right? The half reaction that's producing electrons, the half reaction that's accepting the electrons, okay? The reducing and the oxidizing agents. Okay, so this thing is built. After everything gets connected, and the light bulb and the little diagram lights up, bing, is it at equilibrium? Ida, are we at equilibrium? The little light lights up. Yeah. You almost have to read on in order to answer the question. Because then it says, as time progresses, what happens to the light bulb? As time progresses, what happens to the light bulb? It's going to fade out. You know energy doesn't last forever. So that means the answer to the first one is no. Because it can't be. Because it's getting lighter and lighter and lighter. No, the reaction's progressing. You're going to start out with a nice bright light bulb, a lot of reactants, high concentration. Okay. Time progresses, light bulb gets dimmer. How about the voltmeter? Can you read, where's the voltmeter, Kimberly? In that picture, where's the voltmeter? In the picture.
Oh, in this one right here?
Yeah, that thing that reads what volts? Can you read it? 1.08 volts is what it reads. So that little voltage number is just going to drop as the reaction progresses. So when do you know when equilibrium is reached? It's dead, right? That's when equilibrium is reached. It's not going to do you much good. What is the oxidizing agent in the above reaction? Okay, Andy, we have a reaction there. What's the oxidizing agent? 50-50 shot at this if you're looking at it right. Yeah, copper's going from +2 to 0. No, use the words reduced and oxidized. Copper +2 is getting going from +2 to 0. It's getting reduced. So copper +2 is the, that's how I figured out. This guy's getting reduced. So that's the oxidizing agent then. Okay. Recalling from past chemistry classes, what was an easy way to get delta G for a reaction? Gloriana, yeah, let's see how much chemistry you remember here. What was an easy way to get delta G for a reaction, assuming you have the right table? Yeah, what do you do with the table?
We check to see if you're, well, you flip the reaction according to how you want it. I'm close, aren't I? No?
You're thinking about something, you're thinking of Hess's law.
Oh.
How do you get delta G? Remember, you have a table. Anybody remember? Every single compound known to man has its own little delta G. And then what'd you do to get the delta G for a reaction? You're getting there. You add up the delta G for all the products, add up the delta G for all the reactants, then the products minus the reactants. Remember that? That's all you did. That was the easy way to get delta G. And delta G is really the chemist's friend because it tells you what's spontaneous and not, and what's going to happen. Delta G is always blank, Ricardo, for chemical processes. That will definitely happen. Negative. Has no idea about the speed. Just says it's definitely going to happen. Sooner or later. You can't stop it. It's nature. Balls roll down hills. You just don't know when. Sabina, only for electrochemical reactions. Only for electrochemical reactions do we have this expression. So this is special. What is a numerical value for E cell for the galvanic cell in the photo above? So we have that photo. We're supposed to get E cell out of that. 1.08. It's whatever is read on the voltmeter. If a cell is galvanic, Kelly, if a cell is galvanic, in quotes, so there's a term, it means something, then its E cell is something. Galvanic means what? We have electrochemical cells and we have galvanic cells. We're supposed to be talking about galvanic cells. Electrochemical is, you got to stick in a battery and you have to force this stuff to happen. You have to plug it in the wall. You have to force these reactions to happen. This oxidizing agent will not work unless you force it. That's electrochemical. Galvanic happens all on its own. The light bulb lights up just if you mix the right stuff and put the right stuff in the two half cells. So galvanic means it's just going to happen on its own. It's natural, it's spontaneous. So if that's the case, Kelly, E cell has to be what for all galvanic cells? Positive. She caught it, right? Because you want delta G to be negative for spontaneous stuff. So remember these. These things are golden ideas here. Conventional terminology. All this means the same thing. They ask for, what does the voltmeter read? That's the same as what's the cell potential, what's the cell voltage, what's the electromotive force, what's the EMF, what's the E cell. It all means the same thing. What the what reads? Jackie, what the what reads? What the voltmeter reads, exactly. Okay. Standard reduction potential table. Okay, so they have all these half reactions, then they have a bunch of voltages. There's your volts over here, and here's your half reactions over here. Okay. So they make these tables. Randy, when all concentrations are blank molar, all gas pressures are blank atmospheres, the temperature is blank degrees Celsius, the potential is measured against a standard hydrogen electrode. This is what it looks like. So they actually build these things, Brandy, these half cells, and they put them right next to it, and they connect it and have it connected with a little voltmeter, and then they read the volts. But they have to make sure all these concentrations and pressures and temperatures are what? 1 molar, 1 ATM. Ooh, man, she's on a roll today. Right? Exactly. So all those conditions are really important. Otherwise, you're not going to get these numbers. So that's how you make the table. In a table of standard reduction potentials, okay. Jackie, can you see these arrows here? So that means there's reactants, there's products. For every single one, there's an arrow in there. In a table of standard reduction potentials, all the reactants are blank agents. You can pick one. Like pick this guy. Just pick the bottom one. +2 going to cobalt. So this compound got reduced, so this compound is a oxidizing agent. You can look at that for everything. They're all oxidizing agents. But you didn't really have to look at it, because what's the name of the table? Standard reduction potential. So everything is getting reduced. everything's getting reduced, so everything here has to be oxidizing agents, right? Because that's the name of it.
Why are they oxidizing agents if they're gaining electrons?
Oxidizing agents get reduced.
I see it. They're gaining the electrons. Okay.
Oxidizing agents get reduced. Okay. Yeah, these are the guys that are sucking up the electrons. It would be on this side, right? Where did we go? Oh, and all the products are, anybody? Reducing agents, because they're all getting oxidized. Go the other way. Cobalt to cobalt plus 2. He's getting oxidized. Okay. Use the above table of standard reduction potentials to answer the below questions. What's a stronger oxidizing agent? Now, this whole idea of stronger, remember delta G is minus, what did we say it was? NF E cell. That's your hint to all this. So, what's the stronger oxidizing agent? Iodine or tin? So what you're supposed to do, oxidizing agents get reduced, so that means they got to be on this side. That's where I should be looking for them. Do you see iodine and tin here somewhere? Oh, here's iodine. Where's tin? 1, 2, 3. This guy?
Yeah, third from the bottom.
Third from the bottom. There he is. Okay, so there we're supposed to be comparing these two. Well, what are you supposed to compare? The volts, the E cells. So you look at iodine, he's positive 0.53. Tin is negative 0.14. And remember, somebody said E cell is positive. The more positive it is, the more negative delta G is. So the more spontaneous, the stronger. So which one is a stronger oxidizing agent? Iodine. This listed in that table, what's the strongest reducing agent? The strongest reducing agent, Mal, what would you say? There's a trick to figure this out. Okay. She's on the right track here. Because reducing agent has to get what? Oxidized. So am I supposed to be looking at reactants or products? Supposed to be looking at products. And I don't know, they just don't do this. They don't like to be redundant. They could have a table of standard oxidation potentials. They would flip all these reactions, and what would they do to the sign? Flip them all. They don't do it, so you have to do it, Desiree. So Mel's got on the right track. You pick the guy that's the most negative, okay? But you got to flip the sign. So in other words, you pick the one that's the most positive, but you have to flip all the reactions. So either way that you want to think about this, pick the one that you're talking about oxidation. You can pick the one that's most negative, right? Or flip all the reactions. I like to just flip the reactions because I don't like to memorize stuff. So I'm going to flip all these reactions in my head, and I look for the most positive one. It comes up to be, but what compound?
CO.
CO solid. CO solid is your answer. What is the strongest oxidizing agent? Anybody? What's the strongest oxidizing agent? Mercury 2+. If you see what Andy's saying, you're doing this exactly right. You pick the most positive half reaction. There it is, that compound.
So you ignore the coefficient in front of it, right?
I'm asking for a compound. You don't say, what's your favorite element? 2 carbons. That doesn't make any sense. You say carbon,
Why does
right?
it say 2 mercury? That's weird.
It has to balance it.
Oh, to balance it?
Because look what's on the product side.
So
Polyatomic ion. You better have a 2 out front.
strongest if you divide by 2 or you don't really?
What are you talking about?
I
You
was just wondering the fact that's
You pick this compound.
2H.
Hg plus 2. Why does it have a 2 there? Why does it have to have a 2 there?
Because it's balanced.
What's the product that it forms? Is there a subscript on it?
Yes.
Yeah, so you better balance these half. These half reactions have to be balanced. But if they didn't have,
If it takes 2 of them, it just seems.
right? So that's, I guess, what you're getting at is something that is independent of amount.
Yeah.
Is density is a good example. It's just a property of this compound. Extremely strong oxidizing agent. Okay. For all electrochemical reactions, we have the relation. We talked about that. Good deal. How can this relation be rewritten for when the electrochemical reaction occurs under standard conditions? So we're supposed to be using the table. Do you remember this? Under standard conditions, you're supposed to put a little superscript on stuff. Do you remember this? There's a superscript that looked like what? A little 0. Okay. What are you supposed to put little zeros on in here? E cell, because that you get from the table, because that's what that means. If you put a superscript 0 on here, that means get it from the table. If there's no superscript 0 on there, that means you just read it off a voltmeter, right? So you put a superscript 0 on there. Where else do you put a superscript 0? The delta G. So that means use what to get that delta G? Use tables. Use tables. Okay, so it's pretty much superscript always means standard conditions, but that means, hey, use tables. Okay. They're just being a little picky is all. How are the table standard reduction potentials used to find E0 cell for any reaction? What do you got to do? Let's say you've got some reaction here. All right, something going to something. And you want to get E0 cell for this reaction. What did you have to do? Do you remember? First you broke it up into its half reactions. You break it up into its half reactions. You find those half reactions in the table. Then you add up the E. Delta G is not in this table of half reactions. E cells. Add up the E cells. And if you had to flip the half reaction, well, then you better flip that E0. Okay? What if you have to, do you remember that game? All right? You find the two half reactions. And a trick in doing this was that you knew what had to all cancel, otherwise you screwed up. All the what? All the electrons. This had better end up down here. Okay, so that's a check. That's the same thing. But all those electrons better cancel. Right? Okay, so remember, sometimes you got to multiply through by 3. Other ones through by 2. Do you do anything to these E0s? If you flip the reaction, you got to flip the charge, yes. But let's say I have to multiply through by 6. It's an intensive property. It didn't matter. If you have a little bit of water or a lot of water, it's the same density. A little bit of water, a lot of water, it's the same standard cell potential. So you don't. The only thing you mess with is flipping signs. And we'll try one. Let's try one here. Find delta G0 for this half cell reaction. So here's the reaction. You find the two half reactions, add them up so that the electrons cancel, and you better end up with this thing on the bottom. So find the two half reactions. And they're E0s, standard cell potentials. Here's one. Here's the other. Right. Kind of picked a bad example because you didn't even have to multiply through by anything, right? But Danielle, did you get the positive 0.59 volts in the end? Yeah, just add them up. Right? Electrons cancel out, and then I end up with the exact same reaction, so it works. Right? Copper plus 2, and then because they don't cancel, I've got the copper solid, nickel plus 2, so it works. Is this a galvanic cell, Kimberly? Or is it an electrochemical cell? What do we say? If E cell is positive, delta G will be negative. So this is what you want. This will be natural. This is a galvanic cell. You could build this and it's going to light a light bulb. Don't have to plug it in. Maximum work. What are the units for work? Heck, let's just ask Jeff. He's in PChem. He knows. What's the units for work? Joules. Big J. Okay. So W max is the maximum work that can be obtained from a galvanic cell. If that's the case, and that's the equation for it, what's little n? What's E cell? Heck, we didn't even say what F is. Pick one, Marlena. Identify what any of these would be. How would you get little n, E cell, or F? Anybody help her out? This is a tough question because I'm really prepping you for this thing, for what's coming up. But you haven't applied this equation yet, so it's kind of hard. E cell you get from the E0 cell, I would agree with you. From the meter. There's no superscript 0 on it. So you're going to get that from the voltmeter. How about F? What the heck is F? We haven't even mentioned F. We kind of did, though. That's that Faraday constant, which is how many? 96,485 coulombs, right? So that's what F is. F is 1 Faraday. But that's not going to do you any good. You have to put 96,485 coulombs in there to get the right answers. Kind of, it has to do with all those units we talked about before. N. So you're getting this maximum work out of this battery. It could be a battery, right? You pull this AAA battery off the shelf. There's a maximum amount of work, maximum amount of joules that you can actually get this thing to go. That little car is going to go so far and then it's dead. What's little n? The moles of... Little n is moles. Moles of what? You're getting close. What's going through the little wire that's really doing all the current and generating everything? The electrons. It's the moles of electrons that are consumed. Or the moles of electrons that the battery produces. It's the moles of electrons that are transferred from oxidizing agent to reducing agent. Right? That kind of thing. Okay. So there's what you need to know, I think. So for their reaction, what is the maximum work under standard conditions that can be performed if 63.5 grams of copper is formed? So we have an overall reaction here, right? And the copper is being formed. It's plating out. And what's the maximum work under standard conditions that can be performed if 63.5 grams of copper is formed? So I'd say you just start with the reaction, start with the equation, right? Otherwise you don't even know what to to work on. W max is minus NFE. Cell. Okay. Now they didn't give us a voltmeter reading, right? Should be some more English in here to explain why. But they probably want you just to use what for each cell? The table. Exactly. They want you to use the table. And didn't we already figure that out for this half reaction? Yeah, we came up with 0.59 volts. So this is going to be 0.59 volts. All right. And W max is what we're trying to find. And what will be the units of our answer? Joules. So we'll find that. Okay. How about N or F? Desiree, which one's a little bit easier? F is going to be 96,485. Okay. All that leaves is N. See how the units are going to work out? Because in the beginning we said a volt was what over what? Joules over C's. You multiply it by C's. The C's cancel. You end up in joules. So this will work. N. We need to convert 63.5 grams of copper all the way to what units? Moles of electrons. Okay. Now, whenever we converted, Monica, one compound to another compound, electron doesn't sound like a compound, but it's something different. Convert one thing to another thing. We always needed a what bridge? Mole bridge. That means you need a reaction. Well, what reaction do you have that would have, well, actually, I'm missing a U here, aren't I? For my copper. What reaction do you have available that you could use? Yeah, the copper's in here, but electrons aren't. So that one's not going to be any good. The half reaction. Where'd it go? Here it is. This thing right here. That's your mole bridge that you have to use. So for every mole of copper solid, how many moles of electrons were consumed? 2 of them. The ratio is 2 to 1. Or moles of electrons to copper solid. So go ahead, see if you can get that N. And then substitute it into your equation and get your W. Your big W.
So your final answer should be in joules whenever you put in those units?
Yep. Because a volt is a joule per coulomb. And actually what we're kind of missing here is that F is coulomb per mole of electrons, is what we're kind of missing. Because 1 mole of electrons is this many coulombs. Where are you? 63.546. Did you get, Desiree, did you get an answer? Danielle, did you get a number for this? Can't find your calculator. 1.99 times Okay, essentially 2. Oh, yeah, I didn't even notice that. They're going to pretty much cancel out, aren't they? Yeah, pretty much get 2. All right, and then you put in the 2 up here, and you get, what is the final answer?
Negative 1.14 times 10 to the 5th joules.
Okay. Gloriana, don't you hate negative signs?
Yeah,
Don't you want to erase that negative sign?
just a little.
When you get into more advanced chem, they want to keep track of the energy. And these negative signs become a big deal. Because you have systems, and you have surroundings, and you have all they want to keep track of stuff. Negative just means that the energy was given up, lost. That battery, whatever it is, or this, whatever is supplying 2 moles of electrons, just lost energy. So that's why it's negative joules. You can erase it if you want, but it's not hurting anything. Okay. Does that make sense? Jackie, are you okay? All right. I think this is your homework now. So work together on this. See how far you can get. This is homework. Might as well work on it.
So I'll be drinking a lot longer.
Uh-huh. Danielle was late, too.
I got here at like 1:29. It's not fair.
No, you didn't, because I collected them at 1:30.
Joules. Yeah. Thought we were done.
I'm not done.
Unless the last
Ricardo,
one would be the first
sit down.
time.
Oh, we got to hand out exams, don't we? Forgot about that. So Ricardo's all excited.